Guys, in the previous video, we talked about Hamish Small's lab notebook, and we discussed this whole concept of him thinking that he had it. And then he went to Dow supervisors and he said, look at what I did. And they said, yeah, but it sucks. So no one's going to wait 2 hours in order to get a retention time off of something as small as potassium. So you're going to have to go back, and you're going to have to go back to the drawing board and think about what to do from this point. And I showed you this image from his lab notebook, and I said this is kind of what he saw back in the day as the peaks began to elute out of the ion chromatography system. But you know what? I was able to do better than that. So if you want to see some of the other pages of his lab notebook, well, here's one of those. So I think it's kind of nice to see an actual entry from someone that was working in industry in a real laboratory that is as prominent as Hamish Small is now. And if you kind of take a look at the top and you can kind of make out some of his handwriting, you can kind of see his thought process here. Right? He's talking about means of extending the technique to anion separation. Use maybe something like a low capacity ion exchanger. He talks about a question, how to make a low capacity ion exchanger. And he writes a suggestion here. That way I don't forget. If I come back a couple of years from now and I take a look at what's going on, then maybe this will give me a better idea of what to do. Prepare the fine particle size, anion exchanger. This is how maybe that you would do it, and if I've got time, I'll go back and I'll do it all over again. He also kind of draws a diagram over here to the side. Here's an anion exchanger, and this is basically something that they call Dow X for Dow Chemical Company. The Dow X, you got to think of kind of like the suppressor unit right here in the end. The suppressors were not like the suppressors that we use today. The suppressors are basically like another column that gets attached, right? Because as it gets saturated, you have to take that piece, clean it, and put it back on if you want to reuse it. So sometimes they tried to make these pieces detachable so you can exchange them out. Sometimes they put the stationary phase right on top of the suppressor place. So it's a one-stop shop, and you can just take out the whole piece and replace it with a new piece and a new column, and everything goes on the inside. But this was Hamish Small's kind of entry, and here you see it dated 11/9/1971. All right, here's another picture of his laboratory notebook in the day 2, and this is really talking about the suppressor unit. So up here at the top, Dow X50, a surface sulfonated. He goes on and talks about small particles, anion exchanging. He was able to separate positives, but can you really separate negative based on these technologies? These were all the questions that Hamish was going through to kind of talk about and answer in his laboratory notebook. But again, notice how it looks, right? So you probably have written a laboratory notebook before. You've taken a look at what's required, what should be there, what should not be there. You've taken a look at all of these pieces of information. And again, it's kind of nice to see this up close in person from an actual prominent person. Here's another picture of his laboratory notebook. This was a strip chart recorder. And again, this goes through this whole species of anion separation. What Hamish was doing here is that he was trying to separate two anions from each other. Notice he labeled this peak up here hydrochloric acid, HCl. And then he labeled this peak here nitric acid, HNO3. This was his chloride source, and this was his nitrate source. So this peak represents chloride that carries a -1, and this piece represents nitrate, which carries a -1. So here he was able to show that this technology could also work in the field of anion chromatography. As far as that goes, the anion chromatography stuff is great, but if you take a look, the peaks are not as pretty, right? Especially for the nitrate here. This is not textbook. This is not what we would want to see in a lab. This peak starts off really well, but then it goes through some telling. and you do not want to see that telling present. You would prefer to see it like chloride, straight up and then straight back down. And you don't want to see this lopsided curve that's over here to the right-hand side. So in addition to this excerpt from his laboratory notebook, there was a caption that was placed on it, and the caption basically said this was the first ion chromatogram of anions. So 11/13/71 is when this was dated. So if I go back to his entry of cation separation, we're looking at November the 9th. And within those couple of days, we then see this entry of anions of November the 13th. So about the same week, pretty much, when he was working with anions and cations both. Another story is going to happen here too at the same time. There was a reason that he quickly began working on the anion studies, right? Notice the very first one that I showed you, and the very first dated one that was in his lab notebook was a cation separation. And he took the cation separation, and his supervisors told him, it's great news, but it's not practical. No one's going to wait 2 hours. And he goes back to the drawing board, right, with new resins and new stationary phases. So when Hamish got back to the lab and he began to work on the cation stuff again, another supervisor called him up and said, hey, Hamish, listen, about that cation stuff that you're doing, okay? We had a conversation about it, and it looks like what you're doing is pretty good, and I know that we had a problem with retention times, but could you not do that anymore right now? And Hamish was like, well, why do you want me to stop now? And they said, well, we need you to focus on the anion side. Really kind of target the anions and the negative species, not necessarily the positive ones. And Hamish is like, why? That's kind of how I got my start. I mean, I've been working with these cations from really all the way back into the 1950s. And now you're telling me not to do the cation side anymore? And they said, no. And the reason is because we don't think it's as marketable. The negatives are marketable for us. The anion species. The cations, all of these positives, these are things like your magnesium and your calcium and your potassium, your lithiums, all of the other ones. This kind of stuff, the field is already taken. And that's by atomic absorption, Hamish. So we've just kind of been beat. Atomic absorption is begin to lead the field in the metal analysis. And the cations were all metals, folks. Coppers, magnesiums, calciums. Everything on the inside of the periodic table in the transition metals. Your nickels, your chromiums, all of it. Atomic absorption can do that extremely well. So let's nix the cations for now. And let's take a look at the anions, because we believe that it's a more marketable and more profitable method. And Hamish said, okay, fine. But he had to start all over. The reason is because what he had been working on was cations. And remember, we said that we had a column, and on the inside of this was a piece of lattice, kind of, cross-linkers of polystyrene. And these polystyrenes had on the surface of them sulfonates, SO4s. And that allowed some of the retention to happen with the positive species that was coming through. And Hamish knew at this point, listen, this is not going to work. Because if I put anions through this thing now, all of this work that we had just finished with cations is not going to work for the anions, because these things are negative. And my species is negative. They're going to hate each other. They're not going to go through. So Hamish said, we're going to have to not sulfonate the stuff anymore, people. We're going to have to go all the way back, get rid of the sulfonates, and we're going to have to put something else on in its place. Something positive will have to go on there. All right, well, what was this positive piece? And this positive piece ended up being ammonium, NH4. So you could still use the resin base. You could still go through and use the same foundation that you used for the cation species, but instead of sulfonating those groups, you would just add ammonium to those groups. Well, 1 ammonium, 2 ammonium, 3 ammonium, it doesn't really matter, but you would just put ammonium on the surface, and that would create a positive charge, and that should hold these species back from each other, and then we should still see basically separation that goes on, and the detector should be able to pick it up as long as we have our suppressor unit in place. Well, throughout this time, yes, we used polystyrene, or they used polystyrene back then. Still plausible, worked okay. What they did in the anion, though, is that they found another way to put the ammonium on a little bit better. You know, the polystyrene, you would have to use the styrene, S-T-Y-R-E-N-E. You would have to use that styrene and react it. Sulfonation was pretty easy for it, but what they discovered is that something else could actually be ammonianized, if you want to say that, quartonized, really, a little bit better, and that was divinylbenzene. Divinylbenzene was basically like styrene. I mean, there was hardly any difference at all with it, but there were just two groups of divinyl. Here's di and there's the vinyl, so two of these groups on divinylbenzene. So this worked a little bit better for the protonation, or putting ammonium onto the surface of the stationary phase, and they could put 1 ammonium, 2 ammonium, or 3 ammonium, whatever they wanted to put on it. It would work for them. So polyvinyl benzyl chloride, or divinylbenzene. Both of these worked out extremely well. So this was kind of their first option right here, divinylbenzene. Another option that they did was polyvinyl benzyl chloride. That also worked out well for them, and they had a couple of different choices. Divinylbenzene kind of became the ringleader of the bunch out of the stationary phase choices for the anions at the time, and this was abbreviated with a DVB, divinylbenzene. They could also control the cross-linkage here. Just as with the other one, they could kind of go through, have some control, make sure that the lattice is staying uniform and consistent all the way through the stationary phase, and that way there's no bigger holes and smaller holes throughout the stationary phase as the sample comes through and as the sample begins to absorb all of these components. In addition to all of these problems, not only did they have to change the stationary phase up, now granted it wasn't a big change. I mean, this is kind of staying pretty consistent to the cation side, just a slight modification on the anion side is what they had to do. But in addition to that change, what Hamish Small and his group also found out is that the anions needed a different buffer. The anions didn't respond very well to the buffers that were being used in the cations. And what he discovered is that the addition of NaOH, sodium hydroxide, was actually a little bit better at eluting the compounds and improving the retention times. And this made the solutions slightly basic, right? I mean, we're pumping sodium hydroxide in a little bit of, or in some water, and we're pumping a little bit of through the instrument. This is making a basic environment for all of these compounds, and that was kind of needed to improve the retention times and the peak shapes that he was seeing during that time. Well, NaOH here had a problem, And what they discovered is that the NaOH was contaminated. So they were working with NaOH, 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 and then all of a sudden they get an NaOH solution and they're saying, whoa, 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 wait a minute. This actually led to better results. What did we do differently? And they started looking through their lab book and they said, Hamish, we're not doing anything differently. I mean, what we're doing is the same thing that we've done with all of the other runs. We're making sodium hydroxide, we're running it through, we're pumping it through the machine. We can't really understand why this particular run is better. So we get one fluke that begins to happen. But that fluke, that random mistake, made the elution so much better. So they go back and they start looking at all of these things that could have happened in the lab. And what they discovered is that the NaOH that they used this particular time, they made new mobile phase. And that new mobile phase was with new NaOH. And I'm going to put that in quotes because that NaOH was contaminated. And it had some carbonate, which is pretty common actually, contamination in the solution. And what they discovered from that point is if they added a little bit of carbonate to the mix, then our retention times could increase much better, and they can be separated, and they're prettier, and they're more textbook. And this is what eventually led to the bicarbonate carbonate mix of the mobile phases. This simple little mistake in the lab. And that is what greatly enhanced the mobile phases needed from that point on in the anion exchanging systems that we now use today for ion chromatography. So a lot of stuff's going on here at the same time. There's a lot of moving parts, right? I mean, it first started off with cations, and then on a whim, we get anion studies. Those anion studies came from a slight modification of a stationary phase. There was a mistake in the mobile phase. It just so happened to have carbonate, which made the retention times greatly improve and separate a little bit better. And that led to the modern usage of the bicarbonate-carbonate mobile phase that we still use today in the lab. So, now what happens? He goes back to Dow supervisors. And he says, guys, I think I did it. I think I've created an anion system that uses a suppressor system. I know it's not the perfect suppressor system, but we can improve it. And I've picked out a perfect mobile phase that is very easy to make, that you don't need special stuff with, and we've improved that. And I've also picked out a pretty good stationary phase that we can use on the inside of our columns. And we can make that stuff because we made it in our lab. And we've been using it for who knows how many years. So finally, Dow said, Hamish, good job. And now we want you to attend a seminar. And we want you to tell some folks about what you did. And Hamish said, fine. I'll go. I'll present my stuff that I've been working on. It's in our lab notebook, so if there's any kind of patents or anything else that's out there, we've got documentation of it. And we'll go share this with the scientific community. And Tim Stevens was another scientist that was there. He was slightly young, younger than Hamish. He worked for Dow, and he attended that seminar. And Hamish came in, and he spoke to a group of people, and he kind of started persuading people to use this analytical method. Listen, guys, we've got something going. If you want to separate anions, this is the way that we've done it in our lab, and it works. And we've got a stationary phase down. We've got a mobile phase down. It's very easy to use. It's very easy to make. It's going to make your life so much better. And Tim Stevens was part of that, and Tim Stevens adopted that idea. And he said, you know, I think I could use this maybe in our laboratory too. I mean, I'm working at Dow. So I'm going to take this back to our laboratory at a different location. I'm going to implement it, and I'm going to see if this thing really does work. So he goes back and he tells everybody that he knows. Listen, this is what I found out today. And then the word started to get around. And then Dow decided, I think we can make some money. I don't want to fool with marketing. If we could turn this over to someone else that could market it and allow us to make the stuff, then that's where our money's at. So Dow decided to hire a third party to represent this new IC field. And Dow went to this third party and said, listen, we've got this technology on our hands. We want you to market. We want you to advertise. We want you to go to these other labs and tell everybody that you know. But here's the thing. This system, we want to stay on a polystyrene or a divinylbenzene stationary phase. We also kind of want this system to stay on the caustic side because we know what our mobile phase is and what it needs to be. And we're going to both market cations and anions, but we want you to push anions more because we know cation is really AA. However, if you can kind of tell somebody this can double dip, you might be able to sell it a little bit more. So this third party said, you know, I think this sounds like a good idea. I think that we can take this technology. I think that we will be able to sell this instrument. We'll make the money off of selling the instrument, and you'll make your money, Dow, from the production of the consumables that's needed to make the instrument work. So they went into an agreement. And this third party at the time went under the name of Durham Chemical. And all IC relevant stuff from Dow was turned over to Durham during this time. And Durham was responsible in marketing and sharing the information with everyone else in the labs across the country. There was a man that led this charge. His name was George Rock. Shortly after Durham Chemical began into this tap, they were bought out and they were changed names. And the name of this company that they changed into was called Dionix. And that is the birth of the Dionix Corporation. Now, this is not the first time that Dow did something like this, right? Dow also had other technology prior to this. This was the gel permeation technique. They were, again, working with stationary phases and working with resins, and Dow went with another third-party route prior to this, and that third party was with a man named Jim Waters. And Jim Waters started the Waters Corporation, which specifically dealt with HPLC systems. So Dow had already had this agreement before. Hey, Waters, You sell HPLCs, we sell the consumables for the HPLCs. Match made in heaven. They did the same thing with ion chromatography with a different company, and that was with Dionex that we would associate with today. Dionex now has been bought out by another company. That other company, I believe now, is Thermo Fisher. So Fisher Scientific and Thermo Fisher, kind of sister companies in a way. They are the people that kind of own and manage the Dionex. For this reason, Dionex was the leader in ion chromatography for years and years and years and years. I'm telling you, years worth of it. Dionex was the #1 ringleader in that technology. Now, however, what we're seeing is that Dionex, especially with the switch of the name and the purchase buyout, they have slowly been overtaken. And now Metrome is going to be the person that is becoming the most well-known ion chromatography system in the market. So Dionex is still out there. Dionex is a very common name. You talk to people that have used ion chromatography, they're going to be familiar with the brand of Dionex. But Metrome by far is becoming more and more common. People claim it's easier to use. They stand by their suppressors. It's a 10-year warranty. It doesn't have to stay wet. It doesn't get dried out. The Dionex side of the house, those suppressors are a little bit different. So, for that reason, Metrome is becoming more reliable as well. So, they're putting their money where the reliability is at, where the guarantee is at, and that is with Metrome Company. And that's who we have in our lab. We have Metrome Systems in our laboratory. All right, so finally, we're back up to a current year that we started this whole discussion with, and this was in 1975. So about 4 years after the entry to that lab notebook that you saw, that I basically showed you on the screen, we finally get an American Chemical Society meeting. And this meeting is where IC had its first exposure. And remember, we started this off by saying that the company called Dionex released information about IC. And the company Dow released an article talking about the theory of IC at the same time. And now you understand why. These companies were in cahoots together. And one had the technology basically there with all of the theory and how it works. And Dionex was responsible to market that product and to basically build a instrument that could be delivered out to a laboratory, set up, installed, and basically give training to their employees so that way people could know how to use it. So all of this happened at the American Chemical Society meeting in 1975. Dionex showed up to the convention. They set a table out. They were pushing their product. They were bragging about the first, what they would call, commercial ion chromatography instrument. And then shortly after all of this money started to get raked in, they invested a little bit more in the suppressor unit. And the suppressor began to get improved. So we're not going to talk about that just yet, but I do want you to know in the back of your head, they did go back to the drawing board on the suppressor. They did fix some of the problems that the suppressor unit had. And that's because they were raking in some money. They could afford people to basically put the research in to think about a better suppressor setup. And this began to change significantly in the next coming of years. All right. And now, hopefully, knock on wood, we have it all glitched out. So no more glitches, no more humps, no more mistakes. We've got a system that kind of works, and it works pretty well, and it's reliable, and hopefully it will work for you when you decide to run some samples on it. Okay? As far as the ion chromatography systems, you saw that we had some problems with some nitrates in the beginning, right? Well, those are now cleaned up, but at this conference at the ACS, This is what Hamish and his co-workers basically showed everybody at the convention. Here was the elution times at the bottom. They separated fluoride and chloride and phosphate and nitrate and sulfate from each other. Notice the order of elution's not really going to be the same order of elution that we would see in our laboratory now when we run them. But for the most part, these peaks are kind of textbook. They go straight up, they come straight down. They go straight up, they come straight down. Nitrate's still kind of wonky. We still see a fatter little peak. It looks like it has some slight tailing on it. It leans on the right-hand side. And sulfate kind of looks like it's doing the same thing. It's a little bit of wider peak. It's not narrow. It looks like there's some lopsidedness on the right-hand side. But this was a great improvement. And this was dated about 1975, and it shows a typical anion separation based on the stationary phase and mobile phase that they were using at that time. The mobile phase was down at the bottom, you're seeing a sodium bicarbonate and a sodium carbonate system. 0.003 molarity and 0.0024 molarity. So super tiny. It doesn't take a lot of solid to dissolve in the water to make this thing work the proper way, and that's what we're seeing. All right. So with that said, I'm going to stop the video here, and in the next video we'll continue on with this discovery of the IC system, and maybe we'll get to a little bit of more theory on how this sucker works.